So we're going to look at lesson 13 today. Lesson 13 is just basically lesson 12 again. We're just going to add something onto it. All right. So we know already. Let's just take a look here. Let's figure out what we need to copy here. Yeah. So I think we're going to have to copy this here. We're going to talk a little bit about today polar bonds. We've already talked about polar bonds, right, and non-polar bonds. We talked a little bit about that already in lesson 10, I think. I think it was electronegativity day. So we already know a little bit about bonds, but let's talk about molecules today as well. So how is that going to transfer into these molecules? So we remember electronegativity and recall that EN values can be used to calculate whether atoms have a partial positive charge or a partial negative charge from the attraction of electrons. We'll just stop there and let you copy. So based on electronegativity, we know that sometimes one atom is going to be a little bit negative, one atom is going to be a little bit positive. We'll review that today. But we also have to consider the shape of the molecular compound, and we need to be able to predict whether these compounds are going to be polar or non-polar as a whole. All right. So we're going to use vectors, directions of negative pull. We can predict whether the compounds will be polar or non-polar. This can get pretty complex, so I'm just going to kind of show you, give you a little basic understanding of what this looks like and how this happens, and then I'm going to give you some simple rules to kind of follow here as well. All right, but I think it's important that we understand how some become polar and some are non-polar. I'm going to give you two examples here, and we're going to start with this one here, and we're just going to talk a little bit about what's happening in this molecule here. So the first example I'm going to give you, we're going to try and stick with simple ones here, is carbon dioxide. So you guys can copy that down, carbon dioxide. And we're going to go ahead and draw carbon dioxide. And of course, we know that carbon would have, what, 4 valence electrons. We've done this before quite a few times, yes. By now, you should know that we're going to connect these two together, those two together. And then we're going to make some double bonds here. And we're going to spread this out so it's nice and even and all that. So maybe you want to connect those two there kind of thing. And then these two here, obviously don't do that. That's super messy. And we're going to end up with this diagram here, yes? Okay. By the way, you know this is what? What formula does this represent? Anyone? Huh? Say it out. Can't hear you. What formula would I say for this? AX2, which is linear, which has a bond angle of 180, yes? Okay. So this is AX2, linear, bond angle, et cetera, et cetera. Now, what we're going to do is we're going to kind of break this molecule into parts. So this is going to be a review of, I want to say lesson 10, electronegativity. I could be wrong on that. But this is a review of just electronegativity. So we're going to break this into two sections here. If I just look at this carbon and oxygen here, what's the, let's get our periodic tables out, by the way, because I'm going to need your help here because I forget these sometimes. What's the electronegativity for oxygen? 3.4, okay. So I'm going to put that down here, and this is 3.4, and carbon is what again? 2.6, all right, so 2.6. So again, you don't have to do this. I'm just going to do this for my benefit and maybe yours as well, because this isn't, I can do this. But I'm just going to get rid of this for just a second here. Let's just look at this carbon to oxygen bond here. If you look at those two atoms there, all right, let me ask you this. What kind of bond is that? You have two options, and you need to know this. So we need to review a little bit more. What kind of bond do I have there? You got to know this. Uh-oh. You got two options. Yep. No, don't know what kind of bond. Yep. Yep. Well, it's covalent. Yep. It's more specifically, though. We talked about electronegativity. What? No. Well, it is, but more specific. It is a type of covalent bond. What kind? Look in your notes. Go back to lesson 10. I'm not telling you. Hurry up. You have to know this. We need to review more. That's more than obvious to me. kind of bond is this? Yep. Polar covalent bond, yes, is what I'm looking for here. Polar because these electronegativities are not the same, right? So there's going to be a pull of electrons, correct? Who's going to get the electrons here, carbon or oxygen? Or who's going to pull the electrons towards it, carbon or oxygen? Oh, I don't think this thing's on. Hey, check, check. Check. 1, 2. Who gets the electrons? You got a 50-50 shot. Oxygen, because it's more electronegative. The electrons get pulled towards the more electronegative atom, yes? And if you don't know this, and you're like, what? You better start studying, because we're almost done here, and this is not going to be good. All right? So, the electrons get pulled this way, correct? In fact, we talked about this. What can I do with those two numbers? Subtract them, yes? So this is a force of what? 0.8, I guess. Correct? So electrons are being pulled towards oxygen with a force of about 0.8, right? And in fact, you don't do this, but you could say that this is the partial negative and this is the partial positive, yes? Right? Remember that? Please say yes. Oh. Now I don't know if you're lying. I don't know if you're just saying yes because I said please say yes, or if you actually yes. All right. Don't worry about that part. Okay, we're not going to put that on yet, so we'll leave that off for now, kind of thing. But that's what's happening. Yes. Now we're going to look at the other side of this molecule. So we got double bond O. All right. What's happening on this side of the molecule now? Let's look at this carbon to oxygen bond here, right? Bryden, what kind of bond is that? Polar covalent, yes? So we're going to get electrons pulled this way now, right? We can subtract the numbers again, 0.8, all right? Now those two vectors, yes, if you're in physics class or physics, as I like to call it, and even if you're not, okay, when you have two things pulling an equal amount, what's going to happen? They cancel each other out, yes? Okay, so basically it says, yeah, I want electrons on this side of the molecule, so I want to pull electrons this way with a force of 0.8, but we're also trying to pull electrons this way with a force of 0.8, so they cancel each other out, yes? It's like tug of war. If you put a little ribbon in the middle here, and you're both pulling with the exact same force, what's going to happen? Not much, right? They're going to cancel each other out. Those two forces are going to cancel each other out. So because they cancel each other out, in this case, we call this a you can write this down, polar molecule. Okay? This is a non-polar molecule because those forces are canceling each other out. The pulls of electronegativity, which in this case is 0.8 and 0.8, are the same in both directions. So therefore, they're going to cancel each other out. All right? Is that okay? Now I want to bring to your attention this, and this is kind of important. So look. What kind of bond do we have again here? Bride's the only one that knows this, but what kind of bond? So it's a polar bond, right? This is a polar bond. This is a polar bond. But it happens that those two polar bonds cancel each other out in this case. All right? Now, if I slap a different letter on here somewhere, like instead of an O, if I put an S, then guess what? They might not cancel each other out, right? Because now we have a different electronegativity perhaps there, okay? So is that any questions on that so far? And this is important for us because this is our next column that we're filling in here basically with these compounds. Yeah. Yes. We'll talk about that. Yeah. So it does. Those numbers are pretty similar though. That's the only thing. So when we're talking like 2.6, 2.6, those are going to be, that's, you know, that they're different atoms, but they're probably, I mean, you could make a case that they're going to share equally in that case there, but since the other one's like 2.4, then they're not sharing quite equally there. So you can kind of go either way with those. We don't usually do that just because, but I'll kind of give you some rules as to what's going to happen with that stuff. Okay. All right. Now the next example I want to do with you is good old-fashioned water, and you already know the answer to this. But if we're doing water, okay, I'm going to draw it like this. I hope that's okay. Even if I didn't draw it like that, I'll give you another diagram too, just in case you're like, well, how, you know, that's pretty nice diagram. What if I just did the old-fashioned like this kind of thing? That's fine too. Okay, whatever. I'll do both. Okay, and again, how do we decide if a molecule is polar or non-polar, a molecule? Well, we have to look at electronegativity values. So if I look at electronegativity values, this is 2.2 and 2.2, and if you want to use this diagram here, sure, 2.2 and 2.2, yes. And oxygen is 3.4, yeah, 3.4. And again, if you want to use this diagram here, that's fine, okay? So, again, okay, now we have to understand a little bit about physics and a little bit about that stuff, but again, we'll talk about this. But I hope we understand that, again, we're going to break this into sections, bonds. Just look at a bond, okay? So this H to O bond right here, right? Which way are electrons getting pulled towards, H or O? O, yes. So, and that's getting pulled that way with a force of what? 1.2, yeah? That's a decent force, yeah? Like, you know, remember 1.7 is kind of the magic number there. That's not bad, right? This is pretty polar bond here. And again, if I looked at this bond here, I would say exactly the same thing, right? For now anyway, until we get into some other examples. But that's also going at 1.2, yes? Is that okay? Do you, yes, no? Yeah, just the difference between the two atoms. That's it. That's all I'm looking at. We're not doing anything else. If you want to use this one, it's what, 1.2 and 1.2. Okay. Now, if you're in physics and you're in a certain teacher's class, his class is closer to mine right now. Yes. If you're in that physics class, you've already done vector addition, correct? Who's done vector addition, right? So you know that when you want to add these two vectors together, you need to make some probably right triangles, correct? Is that yes, no? Did you do that? I see this, but I don't know. You make right triangles and then you add the two resultant vectors together. And if you don't know what I'm talking about, relax. Okay. Some people are like, I didn't sign up for physics. This is chemistry. I know. But when you add these two vectors together, I guess the important part here is, you know, are these two vectors going to cancel each other? That's the ultimate question here. Do they cancel each other? In other words, you know, because that's what happened on the last one, right? We know that water is polar, I hope, yes? So they probably are not going to cancel each other, right? If you have two things that come together like this, which is basically this one right here, so this example right here, if you have two vectors that come together like this, do they cancel each other out? What's the net result of that? By the way, if you have two things that run into each other like this, you know, you come to an intersection and two cars are coming together, like heaven forbid, they come together like this, do they just stop in the middle? No, they go what? Up, yes, right? So they'll hit each other and then they'll continue on upwards. Or if you have this kind of situation, right, they're going to hit each other and go that way kind of thing, right? Okay. Does that make sense? So these two get added on together, and you might say, well, you know, like I said, I don't understand physics. Well, we'll get to that part. I'll give you some simple rules for this, but we have to understand that because these forces do not cancel each other out, okay, we're going to get something called a polar molecule. And in fact, these two actually will add together, won't they? Right? So again, what's going to happen is because this force is pulling this way and this force is pulling this way, we're going to get all the electrons are going to get pulled towards oxygen, yes? So we get a partial negative charge, right? And we're going to get a partial positive end to this molecule down here, and one down here as well, okay? So those hydrogens are going to become a little bit positive, okay? In this case, technically, probably, you know, when I say a little bit positive, I mean not enough to be an ion by any means, but they're going to become pretty positive. But again, not enough to make it a positive ion, all right? So same thing with this diagram here. We're going to get these two, all these electrons are coming here, so we're going to get a negative end and a positive end to this molecule. And you can look at it like there's the positive end here, positive, or basically all together you could say that this is positive, and this is going to be the negative part up here. And as a result, because these two forces do not cancel each other out, we get a polar molecule. Okay, so this becomes a polar molecule. Again, we had some polar bonds, like Bryden would say, well, this is a polar bond, this is a polar bond, and in this case, we end up with a polar molecule because those forces don't cancel each other out. They'd add together. If you want to see the complex stuff of that, I don't know, is that okay? Can I move on to the next slide here? If you're in physics, you would see something like this probably, yeah? Like, no, maybe, I don't know. This would be force 1 and force 2, and then you make a little triangle here, I think, is what you do. And then this one here, and then you take this, and you add this, and you get that as the result. So basically, the electrons are being pulled up to here. Yes? Kind of thing? Does that make sense? Yes? No? You're not. You're looking at me like, no. What? Who? Oh, like this? Oh, two beside each other? Oh, well, that's what this part is. But you haven't done sine, cos, or tan stuff? Oh. Okay. Oh, okay. Yeah. Oh, okay. Anyway, that's, like I said, that's not really important for us here, but that's kind of what's going on, right? Those would add together. Yeah, and you guys only are allowed to use a squared plus b squared equals c squared, right? I think, in sine, cos, tan. You should ask to use Coase law, see what happens. Yeah. Symmetry is often going to help us decide whether these polar molecules are polar or not. So remember we had the CO2, CO, symmetrical, and they cancel each other out. H2O kind of didn't look like that. It kind of had like an angle thing to it, right? So it wasn't quite symmetrical. It wasn't the same all the way around. So they give us these two examples here. CCl4 is nonpolar because the C to Cl bonds are all identical and they cancel each other out, right? If we have all the same atoms, they all have the same electronegativities, yes? But if we throw one different on there, CHCl3, then, okay, it becomes polar because it doesn't matter, we change the atom, it's going to have different electronegativity. We're going to then have, of course, a polar molecule. And, you know, I'll just do it. You don't have to copy this down, I don't think. What did I say, Cl? I'm just going to ignore, you know, again, in this case here, right, we have, can you just tell me one of these here? This is 3.4? 2? Okay. And this is 2.6. So we're going to get a pull this way, and a pull this way, and a pull this way, and a pull this way, right? 3.2, 3.2, 3.2, right? And of course, because they're all 0.6, 0.6, 0.6, 0.6, right? Symmetrical, they're going to cancel each other out, right? Does that make sense? Okay. Good. If I, yeah. Doesn't matter. Yeah. If I change one of those, now all of a sudden what happens is this is 2.2, right? And that's not the same force as the other ones. So now it becomes polar because they're not all going to cancel each other out. In fact, if you actually looked at this, just to mess you up a little, most of them are going to get what, 0.6, 0.6, 0.6, 0.4, right? Down. So probably the negative part would probably be, this is going to be partially negative, partially negative. This will be the partial positive end here kind of thing. And maybe even a little bit in this case there, okay? So don't worry about that too much. That's not really, that doesn't really matter too much, but that's kind of what's going on with that molecule there, right? They don't always pull away from the central atom. Sometimes they go into the central atom, okay? But it just depends on those forces. Do they cancel each other out, okay? All right. So I'm going to give you this, and we're going to copy this, then we're done. But I'm going to give you this, and then we're going to talk about one specific molecule here. So let's talk about this here real quick. The simple things are, like, like I said, I know you didn't sign up for physics, so I get that. Basically, it's going to work like this. If the formula that we talked about yesterday, and we're going to do again today, but if the formula is AX2, AX3, or AX4, all right, then and if the X's are the same atom, like for example, CH4, CHHHH, then it's nonpolar. BF3, best friends forever, forever. BF4, BFFF, best friends forever, forever. Oh, I don't know how else to explain that one. You're not all laughing yet. B, remember borons, B is B, and then we got an F coming up, right? And then an F and an F, and remember borons allowed to only have 6, right? That's the exception to the rule. So that's perfect. That's AX3. All the X's are the same. Those atoms that are bonded to the center one are the same. So BF3 is an example of that. CO2, like we did before, AX is the same as this X. So this force cancels out that force. Yes? CH4, CF4, right? As long as those atoms are the same and it looks symmetrical to you, then it should be nonpolar. If it's not that, okay, basically, everything else is polar, all right? So, like, most molecules are polar, right? Everything that's not listed above, we change one of those letters, it becomes polar, right? If there's an E in the formula, like, for example, water, AX2E2. If there's an E anywhere, AX3E, AX2E, it's automatically polar. You do not have to think about vectors or this, it's polar. As soon as you put the E in the formula, your next step is polar, guaranteed, okay? Or, like I said, if it's not one of this is kind of like, this right here is the special case, right? This is like, this set is the nonpolar ones, everything else is polar, okay? Does that make sense? Okay. All right. So we're going to do that real quick here, and I'm going to give you the rest of class to work on that. But I just wanted to ask you this one, and this is a nice little skill testing question here. Now that you know that, okay, polar or non-polar? Think about that for a second. Polar or non-polar? That's an F there, by the way. Kind of messed up. What do you think? Polar or non-polar? How many people think polar? Just put your hand up. Polar? How many people think non-polar? Put your hand up. Okay. All right. How many people don't know anything and they're just refusing to answer questions because it's chemistry class? Just one. Okay. And me. Okay. So, polar or non-polar? Well, let's take a look at this. So, why would you say there was a lot of people pick non-polar? Yes, correct. So what you're saying is, remember, this is 4.0 and this is 4.0. Yes, and I think this is 2.6. Yeah. So I guess the question is, does that force cancel out that force? Okay. Think about that. 2.2 and 2.2. So I guess in this case, we actually have this and that, don't we? Because the electrons always get pulled to the higher number. Okay. Do those two forces cancel each other out? And the answer is, anybody want to, now, who thinks nonpolar? Now. Who thinks polar now? More people are with polar now all of a sudden. Polar people are correct. This is polar. And if we go back to the rules, it actually says this right in the rules, right? AX4, right? All the X's have to be the same atom. But you might say, I know what you're thinking, but doesn't, look, they cancel each other out, right? But they don't. Because what kind of molecule are we dealing with here from yesterday? AX4 is, it's in the notes, AX4, look in the notes, tetrahedral before, and we wrote that down, we wrote down bond angle, we wrote down one sentence, I believe. What does it say there? It's three-dimensional, okay? So that changes things, okay? So, by the way, I know I didn't show you this yesterday, and I don't know how much time we're going to have today because I want you to have time to do some homework here, but this is what CH4 looks like. This is CH4, okay? And again, I can't step across the line. It doesn't matter, okay, which way. It doesn't matter which way you flip it, right? Ding. It's going to be the same, right? It's going to be the same, CH4. So this is nonpolar. But what happens is, this is, by the way, that's the carbon there, and that's what tetrahedral looks like, okay? If we take 2 off, excuse me, so now I put these are the fluorines that I put on there, okay? Now what you have to keep, well, it's still the same shape, obviously. You know, it still looks the same, and it doesn't matter really which way you flip it, kind of thing. But here's the issue, right? When you look at this, you think, well, fluorine's across from fluorine, yes? But is it across from each other? No, right? Remember, what's this bond angle here? Quickly, 109.5, yes? Is the bond angle there, right? And again, the hydrogens aren't across from each other either, right? So that's the issue here, okay? And if we know about a little bit about vector addition, okay, basically, if you think about these two and just isolate these two, okay, these are the 2 fluorines. You might say, well, you tricked me because you drew it like this. Yeah, I did, but I drew it like that for a reason. You know, you might say, well, could I do this instead? And the answer is, sure, you could do that instead. That's fine. But when you look at these two here, remember, they're getting pulled this way, yes? Electrons are getting pulled towards fluorine this way. And if you add this, and if you don't know about vector addition, what I would tell you to do, which is not what the physics guys would tell you to do, is to make another triangle here, because they're the same force, and then use cosine law. That's what I would do, but don't tell them that. But the net force is going to be up. When you pull 2 things like this atom is going to actually get pulled up, right? I mean, there's going to be a force pulling up, whether you think so or not. There is, okay? So this force, whatever that happens to be, going up, then what we have to look at is this force here. And of course, this force, when I do this, it turns out, even if it was this and this, if it was, that's not going to be the same going this way as it is this way, because we got different atoms. So this force is going to be less, probably less, I imagine, because fluorine is the most. So this and this is going to be less. These 2 vectors here are going to be less than these ones, that's for sure, okay? And in this molecule, not only that, this, remember, again, I'm going to flip it over here. This is going this way, this is going this way. The resultant is this, okay? We call it the resultant. I think we call it the resultant, don't we? Yes? The resultant force or vector is this, okay? Going up. If I flip it over, okay, and I still have this going down here, right? There's my down. These 2, hydrogen and hydrogen, are going into the carbon. So we actually get a force that's going this way and this way, okay? So, you know, if I can use this as well here, I don't know if I can. That's yeah, that's my net resultant force so far. And then I got another force that's actually adding on top of that, going into it. So the net result is probably going to be have a very negative end down here and a very positive end up here to this molecule. It's definitely going to be polar, okay? So we have to be careful with these because these are three-dimensional now. And yes, we can draw them to try and trick you, but you have to be like, well, no, because that's 2 dimensions. This is 3 dimensions, okay? Is that okay? So again, it goes back to the rules. AX4 if all the x's are the same. They have to be the same. You know, we can switch 1, it's definitely polar. We can switch 2, we can switch 3, still going to be polar. You know, if all of them are the same, then it's non-polar. Okay, does that make sense? Okay, I'm going to stop talking today. We're still going to do this, I promise, and we need to give you back a quiz, which I think I'll give them back to you, but I'm going to have, I think we'll wait till tomorrow to go over it. I know that's not ideal, but I have quite a few people that need to do it still. So I'll give them back to you, and then we will, and then we'll go over it tomorrow, I promise. Okay. So again, today, don't worry about copying this down. That's just whatever. Today, we're going to basically do exactly what we did yesterday. Okay. We're going to draw, state the general formula in terms of AXE, name the molecule shape, state the bond angle, and then tell me today whether it's polar or non-polar. Today, okay, you might actually have more than one central atom today. So you have to be a little careful with that, okay? So same stuff as yesterday, except we're just going to tell you if it's polar or non-polar. So I'll come back to this because I know some people already know kind of what the stuff to do is there. And these are going to be the shapes that we do here. Okay, so you can take a picture. It's in Google Classroom under PDF stuff for sure. So if you, or you can write them down, whatever, and then I'll move it up here right away, and then I'll go back to the other sheet there too.